Okay, so this is our second day focusing on a different type of FRQ. For this particular one, we're going to look at ones that address F prime, F double prime graphs, kind of typical ideas there. Same thing as the last one. I'm going to work through 4 of them. My recommendation is maybe to watch the video for 1 or 2 of them, and then pause the video, try the next 1 or 2 on your own, and then restart the video to see kind of how you did. You can hear the explanation, grade your problem, that sort of thing. If you felt like you already, you did part of them right, you could fast forward the video, that kind of thing. Because you definitely don't need to watch the whole video if you feel like you're able to answer the problems on your own. A reminder that our goal here is not necessarily to get every single problem 100% accurate. I mean, if you do, great, but that really is not the goal. Remember those skewed percentages. Our goal is with each FRQ to identify 1 or maybe 2, but 1 more point that you think you can get right next time, because with each point that you identify and very purposefully study, process, digest, maybe do a couple of other ones like that one idea, the more you can strengthen that with each 1 additional point, the higher you are getting, and the more into your goal realm, 3, 4, or 5, you're gonna find yourself. So you can't get overwhelmed by trying to understand all 9 points every single time. I want us to see it. I want us to know how they work so you can pick your points appropriately, but you need to release that idea that you're going to get all 9 points every time perfectly. It's just probably not going to happen. Okay? Okay, so first up, ladies and gentlemen, with our F prime, F double prime focus, the place you want to start is what we did back in Unit 3. So I called this the 3.6 lesson. It didn't tie to 3.6 necessarily in our textbooks, but I call it 3.6 because it's looking at kind of wrapping up what we had looked at before then. And at the time, we would have written down on the board a couple of times all of our definitions. And I always write the definitions in kind of a table form after I had a student share this with me a couple years ago, and I really liked how it looked. And I found it works for a lot of students. Now that being said, if you didn't like the table at the time, don't use the table. If you wrote down things differently, continue to do it the way your brain has processed this material, right? But we would have written this down several times, a couple times in class all together, and then I eventually would have had you, okay, now you write down your definitions or quiz yourself on your definitions on your own, and then, checking that with your partner. Okay? So we're going to kind of do a modified version of those 2 ideas here. F, the first thing that we need to know is that when we are asked where F is increasing, what does that mean about F prime? Actually, I don't need to write that. I'm just going to write increasing. Okay, well, what that means about F prime is that F prime is positive. Or some people prefer to think of it as above the x-axis. Okay? What does it mean when F is decreasing? That means F prime is negative, or some people I saw at the time wrote below the x-axis. I also, now that I'm thinking about it, remember seeing some people who, rather than writing increasing or decreasing, drew their arrows. I think there were times where I did both, so drew an increasing arrow or a decreasing arrow. So maybe that's how you prefer to think of it. Okay. Where does F have a relative max? What does that mean? Okay, well, because a relative maximum is where F changes from increasing to decreasing, going up and then coming down, increasing to decreasing, it's where F prime would change from positive to negative. So from positive to negative. Okay. Next up, we have F's relative minimum. What does that mean? Okay, well, relative minimum, where F changes from decreasing to increasing, so where F prime changes from negative to positive. 3 more. Concave up. When f is concave up, what did that mean? Okay, well about f prime, that meant f prime was increasing. It meant f double prime was positive, or again, above the x-axis, if you prefer to think of it that way. Okay, concave down, what did that mean? It meant that f prime was decreasing, or f double prime was negative below the x-axis. And then last but not least, our points of inflection, POI. What did that mean? Okay. Well, that's where f changed, because the point of inflection is where f changes from concave up to concave down, is where f prime changes from increasing to decreasing, or POI is also where f changes from concave down to concave up, so it's where f prime changes from decreasing to increasing. So we are looking at increasing to decreasing, or decreasing to increasing. For f double prime is where we change from positive to negative, or negative to positive. Okay? And so when it comes down to, or comes to your FRQs for f prime, f double prime graphs, this will be your first line of defense. You'll want to look through the problems and identify which of them address these concepts right here. After that, you will usually, I'd say, get at least a couple of additional questions that can get pulled really from any unit, any idea. And so you'll see several of them today. 3 key ideas I want us to jot down again. Well, a couple we wrote down last week on the tabular data day, and then one is a little bit more new for our notes here. When it comes to f prime, f double prime graphs, one idea that you will see fairly frequently, and so you'll see 2 of them today, is an application of second fundamental theorem of calculus. Second fundamental. And you will see this when you are given some function, so that function could be anything. H of x equals the integral from, and we'll do, I don't know, 2 to x of g of t dt, something like that, right? So you're given some function, and your graph will be a graph of g, not a graph of h, but a graph of g. Okay, and then you'll be asked, for example, like where does f have a relative max? Where is f concave down? Like things like that. And so that requires us potentially to be able to need to know the f prime graph. And so kind of rule of thumb when it comes to f prime, f double prime graphs is if you are given a function that is in an integral form, take the time to use second fundamental theorem of calculus to take the derivative. Because remember, that's what second fundamental does. It takes the derivative of an integral. If I plug in the upper, I get g of x times the derivative of the upper, derivative of x is 1, minus plug in the lower, g of 2, times the derivative of the lower, which is 0. And so all of this then simplifies to just g of x. And that's going to be a key piece of information if, like I said earlier, you have a graph of g, because then if I know I have a graph of g, what I'm looking at is h prime, or my f prime column here. And so this will be something that you see with some frequency, and again, you'll practice this twice today, but this is a good rule of thumb, is if you're given an integral within an f prime, f double prime graph form, take the time to take the derivative. Because usually you will be looking at the derivative graph. Okay? And then 2 reminder ideas. We wrote these down the other day. First one is that an integral is a reminder, some total or accumulating idea. For our graphs, we're going to be using more, I'd say, the idea of area. Careful to watch below the x-axis. Remember, that's a negative region. Right? So you've got a negative integral if you're below the x-axis. And then a derivative, as a reminder, is a rate, or for our graphs here, since we're looking at a graph, we're going to be using more, I'd say, the idea of a slope, rise over run, change in y over change in x, something like that. Okay? And again, these are not the only questions you would be asked. With the exception of these ones, which I'd say are typically a little bit more standard, the other questions, there's a variety of questions that could be asked. And so again, you're going to see quite a few of them today. And then we're going to continue to practice them over the next couple of weeks. You are not done with F prime, F double prime graphs today. Okay? So again, I uploaded 4. Like I did with the tabular day today, I'm going to work a little bit out of order. I'm actually going to start with 2015, then go to 2016, then we're actually going to go to 2013, and then end with 2014. Pull that up. Okay. Okay. So 2015 here, we have the figure above shows the graph of f prime. Okay, so when it comes to f prime, f double prime graphs, you always want to make sure you take a hard look at the graph you're actually looking at, because again, when you're thinking about your table, that's going to change what you are looking at to answer your questions. We're looking at an f prime graph here. And I would say like 99% of the time, that's totally a made up percentage, by the way, but a vast majority of the time, you're going to be looking at a first derivative graph. Okay, don't assume. Okay, always make sure to take a look, but I'd say you're frequently going to be looking at a first derivative graph. Okay, so the graph above shows the graph of f prime, the derivative of a twice differentiable function f on the interval -3 to 4. The graph of f prime has horizontal tangents at x equals -1. So I'll go ahead and draw in my horizontal tangent there. X equals 1 and x equals 3. The areas of the region bounded by the x-axis and the graph of f prime on the intervals -2 to 1, so this first one, and 1 to 4, the second one, are 12 and 9 respectively. And so we have to say, nope, that's not 9, that's -9. Nope, that's not 12, that's -12, because they're below the x-axis, and so when we are integrating them, we have to remember to make that negative. We talked about that back in Unit 3, right? Always think for yourself when it comes to the location on your graph. Okay, so A, find all x coordinates at which f has a relative maximum. Give a reason for your answer. Okay, so we are looking at an f prime graph. Goodness sakes. Sorry, 1 second. I don't know why my alarm keeps going off. Okay, make sure all of them are turned off. Sorry, find all x coordinates at which f has a relative maximum. Give a reason for your answer. Remember, we're looking at an f prime graph. Okay, and so when I'm trying to figure out where f has a relative maximum, but I'm looking at an f prime graph, I'm going to be looking for that feature where my f prime is changing from positive to negative, above the x-axis to below the x-axis. Okay, and so as I look at my different points on my graph here, looking for where is my f prime change from above the x-axis to below the x-axis, well, it changes right here at -2. And so f has a relative maximum at x equals -2, and then give a reason for your answer. So reference this last week, but I'm going to say it again. Reason, explain, all of those mean words. Justify can mean work as long as your work is thorough enough, right? I tend to recommend throwing in some descriptive elements even then, if you've got the time. Okay, so x equals -2 because, so why is that where f has a relative maximum? Because f prime changes from positive to negative at x equals -2. Okay? And if you wanted to, you could even explain further, like when f is increasing, f prime is positive. And when f is decreasing, f prime is negative, if you wanted to. You have 15 minutes per problem as a reminder, or at least 15 minutes this year on this problem. And so you're looking at, with 4 parts here, approximately speaking, right around 4 minutes per part, a little bit less, but right around 4 minutes per part. So you have time to be thorough, to really pause and think about your definitions, and to make sure you've answered it correctly, right? Okay, B. On what open intervals, okay, so opens, we're going to make sure we have parentheses, contained in -3 to 4 is the graph of f both concave down and decreasing. Okay, so f concave down, what does that mean for my f prime graph? Well, f concave down means f prime, which I'm looking at, is decreasing. Okay, so f concave down, I want f prime to be decreasing. And then f decreasing means f prime is going to be negative below the x-axis. Okay, and so that's what I'm going to be looking for on my graph. Okay, so where is f concave down and decreasing, aka f prime decreasing and negative below the x-axis? Well, f prime is decreasing on this entire interval here, but it is only below the x-axis, negative, from -2 to -1. And then f is decreasing again on this entire interval, and on this interval, f is concave down, f prime is decreasing on that entire interval. F is decreasing and f prime is negative below the x-axis on that entire interval as well. And so we're going all the way from 1 to 3. And then give a reason for your answer, because f is concave down when f prime is decreasing. And f is decreasing when f prime is negative. F prime is concave down. F prime is decreasing and negative on those intervals. And again, as I said last week, there's a wide variety of ways of explaining this. So my way is not at all the only way. So if you are sitting there going like, can I just write this, or does this work? And you aren't sure, like, feel free to send me a picture of it, email me. I'm more than happy to check that for you. Both of these, by the way, were 2 points. I forgot to say that with part A. First point for both of them came from the answer. So x equals -2 in A, and then your intervals here in B. And then the second point for both came from your reason. Right, so articulating how you know f is a relative maximum, or f is concave down and decreasing. Okay, part C says, find the x-coordinates of all points of inflection on the graph of f. Give a reason for your answer. Okay, so part C, points of inflection of f. What does it mean for f to have a POI? Well, f's POIs on an f prime graph is where f prime changes from increasing to decreasing, or decreasing to increasing. Okay, and so then you'd be looking at your graph going, okay, so f has a point of inflection when f prime changes from increasing to decreasing, or decreasing to increasing. Where does that happen? Well, on my f prime graph here, f prime changes from decreasing to increasing at -1 and at 3. Okay, f prime changes from increasing to decreasing at 1. And so then you'd write that, right? My points of inflection are at x equals 1, because f prime changes from increasing to decreasing. And x equals -1 and 3 because f prime changes from decreasing to increasing. Okay. There we go. Okay, this one was also worth 2 points. 1 for your answers, 1 for the reasons. Okay, so all of those came directly out of Unit 3. So come, like I kind of demonstrated earlier, right off of our table pretty much. Part D is kind of our oddball one for this particular year. It asks, or it says, given that f of 1 equals 3, write an expression for f of x that involves an integral. Find f of 4 and f of -2. Okay, where this one actually comes from, and this is going to be 3 points, is actually out of your particle motion packet, although it's definitely taking kind of a weirder form here. They've given us, oh, that should have an N on it, sorry, given that f of 1 equals 3, they've given us one location of our graph, and they're asking us to find different ones. What this is technically speaking our desired position formula. I've got 1 point and I want a different one. And so our expression of f of x here, f of x is going to equal the desired position formula. My given position, which is 3, my given time of 1, and my desired time, which is going to be some value, with my f prime inside. A desired position formula, we usually call it velocity, but in this case it's called f prime. Remember, velocity is the derivative of f. And we talked about the fact when I walked through that given or desired position formula, and I put it up on the board actually a couple of different ways. And I said that the tricky part about the desired position formula is it's not always going to be called velocity. When we talked about it in class, I said sometimes it's called f, sometimes it's called g. In this case, it's called f prime. So it's not always going to be called velocity here, but the key, as we talked about in class, is that I'm given 1 point, I'm given 1 location, I'm desiring a different one, a different point in time. So that's why I call it the desired position formula. Okay, and so then we are going to use that expression then to find f of 4 and f of -2. So f of 4 would be 3 plus the integral from 1 to 4. And f of -2 is going to be 3 plus the integral from 1 to -2. Which that one's upside down, so I'm going to go ahead and fix it. 3 minus -2 to 1. And then when it comes to evaluating integrals, remember that an integral is some total, some accumulating value. For us, we're going to consider it as area, right? Because that's what we're looking at with this particular f prime graph. And so this is going to be the area from 1 to 4 of f prime. Well, 1 to 4 here was -12. And so we have 3 plus -12. And then for this bottom one, there we go, 3 plus -12. For this bottom one, we have 3 minus, and then -2 to 1. Well, -2 to 1 was -9. And so this is going to be 3 minus -9. A reminder that you do not have to simplify, so you are allowed to leave it there if you want. 3 minus 12, though, if you want to simplify it, is -9, and 3 minus -9 is 12. Okay? Okay, and so 3 points, 1 essentially for each of these. 1 for your expression for f of x, 1 for f of 4, 1 for f of -2. Okay, I'm going to do 2016 next. I would recommend after watching 2016, maybe pause the video, try the 2013, 2014 ones on your own. That way you're seeing how you're doing. If nothing else, make sure you try at least one of them on your own so that you can get that gauge. What are the points I'm going to be focusing on as I move forward with practicing F and F prime graphs. Okay? So 2016, we are looking at, the figure above shows the graph of a piecewise linear function, f, between -4 and 12. The function g is defined by g of x equals the integral from 2 to x of f of t dt. And so this is what I referenced at the very beginning, excuse me, sorry, which is that a good rule of thumb is if you are given a function that's an integral, take a moment to take its derivative. There's a good chance that the graph you're looking at is actually the derivative graph, even if it's not labeled a derivative. It'll be the derivative of h, you know, that kind of thing. And so I'm going to go ahead and do that with mine here. Even though I haven't even read A, I've got an integral. I'm going to go ahead and take a moment and take its derivative. Okay, so g prime then would be second fundamental theorem of calculus, plug in the upper, times the derivative of the upper, minus plug in the lower, times the derivative of the lower. And then all of this simplifies to just f of x. And so this graph up here, which is a graph of f, is also a graph of g prime. Okay, I'm looking at a first derivative graph there. Oh, and I almost forgot. This year, doing the derivative, that process, finding that g prime equals f of x is its own point. And it was interesting this year on the rubric, when you look at the rubric, it says that you get a point for writing that in A, B, C, or D. So it doesn't matter when you realize that that might be something you have to do. If you did that process at some point anywhere, A, B, C, or D, you got a point. Okay, again, just highlighting the importance of taking the time to do that within your FF prime graphs. It doesn't always happen that you're given a point, but it's a good thing to keep in mind. Okay, so A, does G have a relative minimum, relative maximum, or neither at x equals 10? So here's x equals 10 here. So for G to have a relative minimum or relative maximum, what does that mean? And again, remember, I'm looking at a G prime graph. Well, for G to have a relative minimum, G's relative minimum, I want to see G prime changing from negative to positive, below to above the x-axis. G relative maximum, I want to see G prime changing from positive to negative, above the x-axis to below the x-axis. Okay? And then neither would be, well, neither of those two changes. So what's happening at x equals 10? Am I changing from below to above or above to below? The answer is no. And so in this case, G has neither a relative maximum nor a relative minimum, because F prime, or sorry, G prime, not F prime, F, G prime, which is the same thing as F, does not change sign at x equals 10. Okay, B. Oh, sorry. That one was worth 1 point. Well, 2 if you count this derivative process, but 1 point here for your answer with justification. Okay, B. Does the graph of G have a point of inflection at x equals 4? Okay, well, what does it mean for G to have a point of inflection on a G prime graph? Remember, I'm looking at G prime here, F. Well, G has a point of inflection when G prime changes from increasing to decreasing or decreasing to increasing. And so does G have a point of inflection at x equals 4? AKA, does G prime change from increasing to decreasing or decreasing to increasing? Well, here's x equals 4. G prime does change from increasing to decreasing. And so yes, x equals 4. is a point of inflection because G prime, which is the same thing as F, changes from increasing to decreasing. At x equals 4. Okay, and that one was another point for your answer with justification. Okay, so those were our two what I would call straightforward problems for this one. So you had a total of 3 points at this point. The last two are the ones that I feel like were a little bit weirder. Although I will say part C does get asked with some frequency, but I should say they don't come directly from our table, right? So C says find the absolute minimum and the absolute maximum value of G on the interval -4 to 12. Justify your answer. Okay, so where this one, and this could be a total of 4 points, by the way. So this one's a hefty problem in potentially partial credit or if not full credit. So this one comes out of 3.1 is where we looked at absolute minima and absolute maxima. Your first 2 points in this problem come from identifying values that you would need to test. Back in 3.1, I called it a candidate test. So if you look in your 3.1 notes, you'll remind yourself of the fact that absolute minimum and absolute maximum occur when either the derivative equals 0, so that was the first thing we did is we took the derivative and set the top and bottom equal to 0, or the endpoints, which in this case are going to be -4 and 12 for this particular problem, -4 and 12. And then we tested each of those values by plugging them into our original function, whatever our original function was. So your first 2 points in this particular case come from considers, and then your first point comes from considers that the endpoints might be the location of your absolute maximum or absolute minimum, which is, again, kind of going back to that idea that anything you can think of related to the problem, write it down. If you were sitting looking at this problem going, man, I don't remember like exactly how to do it, but remember that an absolute minimum or an absolute maximum might occur at -4 or 12. Then write that down. Do something with that idea. Write down that it might be at -4 or 12. Try to plug the -4 or 12 into something. Excuse me. But do something, right? You get 1 point for just considering that the endpoints might be the location. The other point came from considering 2 very particular other places. Okay? So the other place that an absolute maximum or an absolute minimum might occur is when the first derivative equals 0. Well, remember, we're looking at the first derivative graph. And so my first derivative equals 0 at -2, 2, 6, and 10. And so if you considered all 4 of those points, you got that second point. Now, you don't actually have to, in this particular case, consider 2 or 10. And so if you left those out and only considered -2 and 6, you still got the point. The reason we don't have to consider 2 and 10 is because they are neither a relative maximum nor a relative minimum. And so they would not be either the absolute maximum or the absolute minimum. But if you were sitting there going, I'm just not comfortable making that assessment on my own, then test 2 and 10 as well. That's fine. As long as you tested -2 and 6 within your process, you got your second point. So again, 1 point for testing -2 and 6, 1 point for testing -4 and 12, considering those locations as potentially accurate locations. Okay? So even if you didn't know how to actually do the test, you'd still have gotten 2 points from knowing essentially the definition of absolute extrema. Your last 2 points come from your answers with your justification. In this case, I'm going to let my work count because my work will be thorough enough to show that. And so we need to be able to test each of those places. What is g of negative 4? G of negative 2. Maybe you test g of 2 as well if you wanted. Or if you wanted to cross that one off because you were like, oh, that's neither an absolute or relative maximum or relative minimum, so it won't be an absolute maximum or an absolute minimum. You don't have to test g of 2. G of 6. Same rationale for 10. And g of 12. And remember, all of these get plugged into your original function. Well, my original function was the integral from 2 to x of f of t dt. So they're getting plugged into this x spot up here. Okay, so negative 4, we have the integral from 2 to negative 4 of f of t dt, which is upside down. So this is negative 4 to 2 of f of t dt. And negative 4 to 2 is this little triangle below the x-axis. So 1/2 base of 2, height of 4, and negative because it's below. And then the rest of the way to 2 is this triangle here, 1/2 base of 4, height of 4, positive because it's above the x-axis. And so negative 4 to 2 is negative. And then my triangle below the x-axis, negative 1/2 base times height. And then my triangle above the x-axis, 1/2 base times height. Which simplifies to negative, and then negative 1/2 times 2 times 4 is negative 4, plus 8, which is 4. And so this is negative 4. And then you repeat that process for each of them. So 2 to negative 2, again upside down, so we're going to go ahead and flip that. Negative 2 to 2. So negative 2 to 2 for this particular graph is only that big triangle above the x-axis, so 1/2 base of 4, height of 4. So 1/2 base of 4, height of 4, which is negative 1/2, 4 times 4 is 8. G of 2, the integral from 2 to 2 of f of t dt, which comes directly out of 4.3, that is 0. G of 6, integral from 2 to 6 of f of t dt. Well, 2 to 6 is this triangle above the x-axis, 1/2 base of 4, height of 4. So 1/2, 4 times 4, which is 8. G of 10, the integral from 2 to 10 of f of t dt, which is the big triangle above, 1/2 base times height, 4 times 4, and another matching triangle, I should say, below, base of 4, height of 4, below the x-axis, so that'll be negative. So we have the above and the below, so negative. And because those are equal areas, so 8 plus negative 8, that's going to be 0. And then last one, we have all the way to 12, which are those same two triangles from to 10, the one above, so 1/2, 4, 4, negative 1/2, 4, 4. But then one additional little triangle at the end, so all the way from 2 to 12, two matching triangles, and then this little guy at the end, 1/2 base of 2, height of 4, and negative because it's below the x-axis. So base of 2, height of 4. And so this would simplify to 8 plus negative 8 plus negative 4, which is negative 4. Okay? And so then of your values here, negative 4, negative 8, 0, 8, 0, and negative 4, my absolute maximum is 8 in this particular case, my G of 6. And my absolute minimum is, and in this case, my smallest value is negative 8, my G of negative 2. which all of that work gets me 2 more points. And it is a lot, so it did take us a long time, but the nice thing is that you've now actually done all of the work you need for letter D. So while it seems like C took a long time, and it does, absolute extrema are not short. Don't let that stress you out. A lot of times it'll be because some of the other problems are going to be on the shorter side. And maybe initially with absolute extrema, when you read a problem like this, you go, I'm going to jot down where they could be. Maybe grab those first 2 points we talked about, jot down your end points and your zeros, and then maybe you move on and come back to it when you've got more time, because it is a lot of time for those last 2 points. But it's a very similar process every time, so it might be something you want to do. Part D is worth our last 2 points. Part D says, for -4 to 12, find all the intervals where my g of x here, and we've just found a bunch of those, is less than or equal to 0. Where is it less than or equal to 0? And so again, you've found all of those values, because as you were working through this, you found where g equals 0. G equals 0 at 10 and at 2. And so what you've got here almost is a kind of a modified number line, right? We're negative up until we're 0, then positive till 0, then negative. And so you could actually, like I said, almost draw this out on your number line. Put 10 on my number line, which is one of my zeros, 2 on my number line. I'm negative when I'm less than 2, positive between 2 and 10, and negative again past 10. So you've got like a little modified number line there. So where is g of x less than or equal to? So we're going to be brackets here, right? Brackets on the -4 and the 12 as well. We are less than or equal to from -4 to 2, and 10, which is where I'm equal to 12 to 0 again, to 12, which is the end of my interval. And so you got 2 points, 1 for each of those intervals. Okay. Okay, so we're going to do 2 more here. Again, my recommendation, pause the video, try them on your own, or maybe you want to watch 1 more and then pause the video. That's your choice, although I would recommend pausing the video now, giving them a shot, and restarting it when you're ready. We're going to be doing 2013 is what I want to do next. So 2013 next. Okay, go ahead and pause the video if you're going to do so. Okay, so for this one we have the figure above shows the graph of f prime. Again, let's go ahead and take note of that. Again, make sure you're very purposeful to identify it. The derivative of a twice differentiable function f on the closed interval 0 to 8. The graph of f prime has horizontal tangent line at x equals 1. Draw that in, x equals 3, and x equals 5. The areas of the regions between the graphs of f prime and the x-axis are labeled in the figure above. So we have 2, 6, 3, oh, nope, -3. And 7. The function f is defined for all real numbers and satisfies f of 8 equals 4. So I've got a point here. As we talked about in the, I think it was the 2015 one. Yes, it was the 2015 one. A lot of times that starting point will end up becoming some sort of desired position formula. So given position, given time, with a desired time. In this case, again, it's not called velocity for this function, it's called f prime, but as we talked about in class, it can be called anything. Okay, sorry. A, find all values of x on the open intervals 0 to 8 for which the function f has a local or relative minimum. Justify your answers. So, local or relative minimum here. Where does f have a relative minimum? Well, f has a relative minimum when f prime, which is what I'm looking at, again I'm looking at an f prime graph here, f has a relative minimum when f prime changes from negative to positive, below the x-axis to above the x-axis. And so where do we see that? We see that occur right here at x equals 6. Okay? And then justify your answer again. Justify could mean work. In this case, there's not really any work to show to support my answer, so I'm going to use words. Justify can be either one. Explain has to be words. Justify can be either. X equals 6 because f prime changes from negative to positive. Positive, sorry. P. Positive. And then maybe you want to, if you got the time, meaning f changes from decreasing to increasing. Get 15 minutes per FRQ, generally speaking. So this one, 4 parts, means about 4 minutes to answer part A, approximately. Okay, B, determine the absolute minimum value of f on the closed interval 0 to 8. So this one's going to tie most closely to the 2016 one, part C. And we talked about on that 2016 one, maybe you, initially speaking, you look at your absolute minimum and you're like, oh, I know those take me a long time. And so maybe you start by just jotting down where you think your values would be. Oh, by the way, part A was worth 1 point. And then maybe you skip the rest of part B and you move on. And so we'll actually do that. Let's go ahead and jot down where our values could be in this case. So remember, absolute maximums, absolute minimums come out of 3.1. The first place you always want to make sure you consider are 0 and 8. Because those are your endpoints. And then the other place would be your 0 and 8. The other place would be where f prime equals 0. And so for this one, this would be 1, 4, and 6 are where my f prime equals 0. Now in this particular problem, you actually only have to consider 6. Although if you considered all 3, that's fine. But the reason you only have to consider 6 is because we're trying to find absolute minimums. Well, 1 is neither a relative max nor a relative min, so it's not going to be an absolute max or an absolute min. And 4 is actually, technically speaking, a relative maximum because f prime changed from positive to negative. So if it's a relative maximum, there's no way it's going to be an absolute minimum. It's not even a minimum to begin with. And so you don't actually have to test 4 if you don't want to. You could get away with just testing 6. You got 1 point in this one for considering 0 and 6. If you also considered the others, that was not a problem, but you had to have considered at least 0 and 6 to get that point. And so we'll come back and finish this one. There are 2 more points that come from all the work in this problem, but we're going to go ahead and move on because, again, that's kind of what I'm anticipating people might do initially with a problem like this, FRQ. Now let's go ahead and take a look at C. On what open intervals contained between 0 and 8 is the graph of f both concave down and increasing? Okay, well, for f to be concave down on an f prime graph, what does that mean? Well, f concave down means f prime is decreasing. And for f to be increasing on a f prime graph, what does that mean? Well, f increasing means f prime is positive above the x-axis. So when they're asking us where is f both concave down and increasing, they're asking where is f prime decreasing and positive. Well, f prime is decreasing and positive from 0 to 1 and 3 to 4. And again, we are doing open intervals, so we're going to write those as parentheses. So 0 to 1 and 3 to 4. And then explain your reasoning. So this does have to be in words because f prime is decreasing, meaning f is concave down. and positive, meaning f is increasing on those intervals 0 to 1 and 3 to 4. Okay, this one was worth 2 points. 1 for your answer, 1 for your reason. Okay, and then part D is another one of our kind of out there ones. It's going to be worth 3 potential points. This one actually comes out of Unit 2, so this would be out of 2.4. Or you could also look at your fall final. We did ones kind of similar to this during our fall final review. And so if you have those notes or want to go on my website and pull those off, you could. It would be another resource. They have the function g is defined by g of x equals f of x cubed. If f of 3 is negative 5/2, find the slope of the line tangent. So what does slope of the line tangent mean again? Well, slope of the line tangent is your derivative. So find the derivative, right? Remember, a derivative is slope. So find the derivative of g at x equals 3. Okay, so derivative of g first. Okay, in this case, the reason this comes out of 2.4 is because this is chain rule here. If we bring down that 3, leave the guts alone, subtract 1 from the exponent, times the derivative of the guts. Derivative of f is f prime. And that process right there was worth 2 points. We haven't even done anything with the add x equals 3 yet. We've literally just applied chain rule, and you got 2 points from that. Plugging in 3 then, we have 3 times f of 3 times f prime of 3. Okay, well, f of 3 is negative 5/2 times f prime of 3. Well, they didn't give me f prime of 3, but what did I start out with? I started out with a graph of f prime. I'm looking at f prime. So when I want f prime of 3 is 4, right? F prime of 3 is 4. And then remember, you don't have to simplify anything, so I'd leave it there. That gets you your 3rd point. If you did simplify, you would need to make sure that it's simplified to 75. 3 times 25 over 4 times 4, so the 4s would simplify. 3 times 25 is 75. But I wouldn't do that. It's a waste of time, and if you make an error, you've now lost your answer point. Okay, so we've gone through, we've gone through A, C, and D, so we're going to go ahead and go back to B and finish that one up because we have 2 lingering points here, which comes from testing our values. So remember, we got 1 point already from articulating 0 and 6 were possible places. Again, absolute extreme occur at endpoints or zeros of f prime. Okay, so f of 0, evaluating that, we need to plug our 0 into our original function. Now, unfortunately, I was not given an original function of f. However, I was given one location of f, and I'm now desiring a different one. That's this desired position formula. My given position, my given time, my desired time, which in this case, first case is going to be 0, and then of my f prime graph. Okay, so we have 4 plus 8 to 0 of f prime, which is upside down. So let's go ahead and fix that. So 4 minus 0 to 8, which is 4 minus, and all of the areas, remember that's what an integral is. Integral is area. So all the areas from 0 to 8. So we have 2, 6, negative 3, this is below the x-axis, and 7. So 2 plus 6 plus negative 3 is 5, plus 7 is 12. 4 minus 12 is negative 8. Okay, and then you repeat that process, f of 8. Now f of 8 they actually gave us. F of 8 is 4. F of 6, 4 plus the integral from 8 to 6 of f of prime dt. 4 minus, fixing that integral, 6 to 8. Which 6 to 8, that interval there is just this region, 4 minus 7, which is negative 3. And then maybe you also tested 1 and 4, maybe you didn't. Again, that depends on how comfortable you are with eliminating them. If you did test them, 8 to 1 would be 4 minus 1 to 8. Which is 4 minus 1 to 8 is the 6, negative 3, and 7. 6 plus negative 3 plus 7, which is 4 minus 6 plus negative 3 is 3 plus 7 is 10, which is negative 6. And again, maybe you tested the 4, 8 to 4 of f prime of t dt. 4 minus 4 to 8. And then 4 to 8 is this region here, so 4 to 8 would be the 3 to 7, or negative 3 I should say, negative 3 to 7, which is 4 minus negative 3 plus 7 is 4, which is 0. Okay, and so we're trying to find which one of these is my absolute minimum. Well, negative 8, 4, negative 3, negative 6, 0, which one of those is smallest? And in this case, my smallest one is the negative 8. So absolute minimum which is at f of 0. Okay, so your two remaining points for that problem were for your answer, f of 0 equals negative 8, and your justification, which is all of your work. Okay. So again, it's absolute extreme are not, I would say, a short process. Myself, when I work through FF prime, F double prime graphs, I do exactly what I just modeled, which is when I read an absolute extreme one, I jot down my candidates that I know I will end up testing eventually, and I move on. I answer all the rest of the problem that I feel like I'm able to answer, and I come back and I do this at the end, because if I'm going to run out of time, I'd rather lose 2 points that have a lot of work, that are potentially speaking quite a few things to test, versus 2 points or 3 points like in part D here, which come from a pretty straightforward derivative. I really don't want to lose those points. Those are ones I feel like I can snag pretty quickly, or the 2 points here in part C, which come directly from your table. And you might disagree. Maybe you like doing the absolute extreme, and so that's going to be what you do first. That's where you have to strategize what's going to be best for you. Okay, one more here, 2014. Go ahead and pause the video, give this one a shot, and restart it when you are ready. Okay, the function f is defined on the closed interval -5 to 4, so you got a function of f here. The graph of f consists of 3 line segments and is shown in the figure above. Let g be the function defined by g of x equals the integral from -3 to x of f of d dt. And so I'm looking at this going, oh, that's that second fundamental theorem of calculus idea. So before I do anything else, I'm going to go ahead and do my second fundamental theorem of calculus. Take the derivative. So plugging in the upper, we have f of x times the derivative of the upper, which is 1, minus plugging in the lower, f of -3 times the derivative of the lower, which is 0. And so g prime of x, if I simplify this, equals f of x. And so I am looking at g prime. Okay? Part A says find g of 3. So interestingly, this one of our kind of oddball questions here actually kind of kicks off our problem. This one doesn't actually come out of Unit 3. This one actually, technically speaking, comes out of Unit 4. 4.4 technically speaking, if I remember correctly. Oh, it might have been 4.3. So we'll put both 4.3 or 4.4 is where to check. It is worth only 1 point, which is for finding g of 3. So what is g of 3? Well, I've got g of x, so g of 3 would be plugging 3 into x's spot. The integral from -3 to 3 of f of t dt. Okay, well, back in Unit 4, we looked at what an integral is, and we wrote that down at the beginning of this session here. An integral, remember, is area. It's a total or accumulating idea. It is area. And so -3 to 3 would start here and go 1, 2, 3 to 0, 1, 2, 3 to this point in time. And so we're finding that area or that region here. So -3 to 2 is 1/2 base of 5. Height of 4. It's above the x-axis, so it's positive. And then we got this little itty bitty triangle here. 1/2 base of 1. Height of 2. And it's below the x-axis, so that's negative. One more time, you do not have to simplify. And with a problem like this one, I wouldn't. It was only worth 1 point. Right? So you have no room for making errors, unfortunately, in Part A, meaning you have to get that 1 point completely right, and so don't simplify because you've got it. This is enough. 1 point. If you simplify wrong, you lose the only point possible on this problem, Part A, I should say. So don't simplify. But if you did simplify, this simplifies to 10 minus 1, which is 9. But again, it's a waste of time. No reason to. Okay, B. On what open intervals contained in -5 to 4 is the graph of G both increasing and concave down? There we go. That's the one we're kind of expecting coming from our table here. G increasing, G concave down. And remember, I'm looking at a G prime graph. So what does that mean? G increasing means G prime is positive above the x-axis. G concave down means G prime decreasing. And so where is this true? Where is G prime both positive and decreasing? Well, we are positive and decreasing from -5 to -3 and from 0 to 2. Okay? And then again, these are open intervals, so we are going to express those as parentheses. So -5 to -3 and 0 to 2. And then give a reason because G prime is, or G prime, which is F, is positive meaning G increases, and decreasing meaning G is concave down on those intervals. Okay, this one was worth 2 points. 1 for your answer and 1 for your reason. And again, remember there are other ways you could potentially write your reasoning, so don't feel like you have to write it like me. Again, if you're not sure, feel free to take a picture of it, send it to me. I'm more than happy to check it for you. Okay, our last 2 parts here are both worth 3 points. And they both come out of Unit 2. So these ones are most similar to 2000. Oh, it actually looks like the one we just did, 2013, letter D, if you're wanting to see another one that's kind of like this. So C comes out of 2.3, technically speaking, or again, your fall final review, because you actually had one very similar to C there on your fall final. D comes out of 2.4, or again, fall final review. Okay? So, C, the function h is defined by that. Find h prime of 3. Okay, so I need to take the derivative. This is quotient rule, so we have low, 5x, d high, g prime of x, minus high, g of x, d low, 5, all over low squared. And that's 2 points that you just earned just for taking the derivative. Your last point comes from plugging in 3. So we have on top 5 times 3 times g prime of 3. Okay? Well, remember I'm looking at g prime up here. So g prime of 3, here's 3, is negative 2. Because that's that coordinate point there. So g prime of 3 is negative 2. Minus g of 3. Well, you actually found g of 3, letter A. If you did, by the way, make an error in letter A, so say you got 5 as your answer, whatever. If you used 5 down here in part C that we're working on right now, you would not lose your answer point because you're basing your work off of previous work that you've done. But I'm going to go ahead and plug my answer in, which is this 1/2 5 times 4 plus negative 1/2 1 times 2. So 1/2 5 times 4 plus negative 1/2 1 times 2. That's my g of 3. And then times 5 over 5 times 3 squared. And again, don't simplify. It's a waste of time. If I remember correctly, this one simplifies to negative 1/3, but leave it alone. You've got your point. Okay? And then D, 3 more points. 2 more points come from taking the derivative because we again have this slope of the line tangent, which is m or derivative. Remember that is what a derivative is. It is slope. To the graph of p at negative 1. So we need to take the derivative of p. This one comes out of 2.4. It is chain rule. Okay, so derivative of the outside would be f prime. Leave the guts alone. Times the derivative of the guts, which is 2x minus 1. That's 2 points. And then your third point comes from plugging in negative 1. So we have f prime of negative 1 squared, which is 1, minus negative 1. So plus 1. 1 plus 1 is 2. And 2 times negative 1 minus 1 at the back. So the question then becomes, well, what is f prime of 2? Okay, well, I've got f. I'm looking at f here. So what is f prime? Remember, f prime is a derivative. What is a derivative again? Derivative is slope. And so f prime on this f graph is the slope of f, in this case at 2. And at 2 here, my slope is down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So my slope is negative 2. And then don't simplify. You've got your third point just by plugging that in. If you did simplify, it simplifies to 6. Okay? Okay, so those are f prime, f double prime graphs. Again, you're going to continue to see them over the next couple of weeks as we continue to practice FRQs. Let me know if you have any questions.